Just as a quick recap, we finished last time, we talked a lot about heat capacity, about latent heat, and then I gave you this chart that looks something like this. That was a graph of how much or how the temperature of a system changes when you add energy to it. So we're going to kind of change gears. And so what we did last time is we talked about how energy entering or leaving a system affects that system. But what we haven't talked about is we haven't talked about how energy goes between systems, right? That's not something that we've done. So we're going to begin today by talking about heat transfer and how that works. So this is section 5.4. By the way, if you haven't seen this notation, this like integral symbol with a circle, that means section. So generally, heat, and this is a generalization. One moment, I have to fix the camera because it's very smudgy. Sorry, it was bothering me. Generally, and again, like I said, this is a generalization, but generally heat can be transferred in roughly 3 different ways. So we're going to talk about all 3, but one of them we're not going to go into a whole lot of details on. So the first is conduction. Now, conduction is the type of heat transfer where 2 things are touching each other. So we're going to analyze what happens when 2 things touch each other. So to do so, we're going to imagine, and this is not a perfect model, but it's good enough. We're going to imagine that molecules in a solid are being held together by springs. Now, they're not held together by springs, they're held together by molecular bonds, but we can roughly approximate those molecular bonds as springs or as harmonic oscillators. So the picture is, you know, your solid might look something like this if we were just looking at a 2D slice. You'd have a whole bunch of atoms, and they'd be connected by springs, like so. And so then they can oscillate back and forth, and they can jiggle each other, and so on and so forth. And so in particular, if you were to start shaking up one end of this matrix of springs, eventually the other end would start shaking, right? Like the motion would transfer. And in fact, depending on the material, that motion can actually propagate as a wave. Generally, it doesn't. It actually generally propagates as diffusion, but there are some substances where that type of motion will propagate as a wave, just leaving that out there. So suppose that we have a rod, a solid rod, touching a stove on one end and an ice cube on the other. So here we have, and pardon my poor drawing, so we have our stove on one end. It's just a cube with a bunch of circles on it. It's hot, very hot. And then we connect it to a large rod. Now this rod is a solid. I'm just drawing it as large, it doesn't have to be. But we can imagine it as made up of a whole bunch of atoms that are connected by springs. Right? Because it's a solid, so its atoms can be approximated that way. And then we put on the other end, we put one of these weird ice cubes that has a hole in the middle, whatever it is. This is supposed to be an ice cube because I don't know how to draw an ice cube otherwise. I guess I could draw like one of these guys, but that's, anyway, it's neither here nor there. So we know that the particles on the left are going to vibrate more than the particles on the right. So the particles on the left, these are the particles in the stove, or the particles in the stove touching the rod, are going to be vibrating more. So they're more likely to bump into the particles in the rod. And so then the particles on the left side of the rod are more likely to be jiggling quickly, whereas the particles on the right end of the rod are more likely to be jiggling slowly. So then the question is using this sort of model, and let me put this out, then it looks like it's actually touching. Using this sort of model, can we figure out, roughly anyway, how quickly the energy that goes into jiggling the particles on the right or on the left side of the rod gets transferred to the particles on the left, sorry, how quickly the energy that goes into jiggling the particles on the left side of the rod transfers to the right side of the rod to heat up the ice cube. And by the way, every time a particle from the stove hits a particle from the metal rod, that particle from the stove loses a little bit of energy, and the particle on the rod gains a little bit of energy. And so the stove is going to cool down, and the rod is going to heat up, and that heat will spread along the rod because it's jiggling atoms along the way. And then it will eventually get to the ice cube where the fast particles in the rod will bounce or will bump into the slow particles in the ice cube, and it will heat up those particles by bumping into them and transferring energy along the way. So that's how this conduction works physically, but we can actually do better than that. We can ask and indeed answer, how fast is the energy transferred? Or transmitted, I suppose. So we're going to work infinitesimally because everything's constantly changing. You have bits of heat or bits of energy moving continuously through the rod, and you have temperatures continuously changing. So we're going to work infinitesimally. So we're going to consider each element, each slice of the model in turn, or each slice of the rod, maybe. So we have one part of the rod, one slice, has some thickness dx, say. It's a really small slice. And the rod will have cross-sectional area A. That's a good thing. We may as well represent that because that might matter. And let's say that the piece of the rod on the left side is hotter because it should be. It's touching the stove. So the temperature should be the temperature plus some small extra amount. Then the next piece of rod, the piece next to it, also with length dx, would just have temperature T. So the point is the piece on the left is slightly hotter than the piece on the right. The pieces are really narrow and they have some cross-sectional area A. So then the question is with this model, can we figure out what will affect the rate of heat flow? And we can probably guess some of these. In fact, I suspect that you probably could. So does anyone want to shout out, before I start giving them away, shout out one thing that might affect the rate of heat flow? Either shout or type. Yeah, so let's start with, so the material certainly will. A certainly will as well. So let's start with A. Yeah, thickness is A. So A, also known as cross-sectional area, the cross-sectional area speeds up, or how do I want to write this? More cross-sectional area speeds up the heat flow. And that's kind of intuitive. The idea is that there's more pipes for the heat to flow through. There's more of these jiggling things that can transfer heat to the next one. And so this implies that the rate at which the heat flows, so Q is the amount of heat flowed. We want the rate at which it flows. So dQ dt would tell us the rate. This should be proportional to the cross-sectional area, right? Okay, somebody else also said composition. So I'm actually going to leave that one for last because it's just the way the composition comes into play is just through material properties, and that certainly will play a role, but there's not really an intuitive way that we can understand that from this model. So what would be another example? What would be another possible way that would, or possible thing that could affect heat flow? Specific heat capacity won't affect, well, okay, it will affect heat flow, but only indirectly. Yeah, so length is another good example. So a shorter length would mean that the transmission is faster, right? There's less distance to cover. So for the same amount of thickness and the same materials and the same everything, if your length is shorter, the heat doesn't have to go as far. So it would certainly be faster. So what we can say is that the rate at which the rate of heat flow should be proportional to the inverse of the length. Now, the length is just dx, so let's just do 1 over dx. Okay, what would be another one? Well, so yes, so Mihika, yes, but in how do we quantify? So you're right, we could write dq dt in terms of q, but that's less useful because then we have a differential equation to solve. In terms of the variables that we know, yeah, it's the difference in temperature, right? So a higher temperature difference will also increase heat flow, right? And that's precisely related to the amount of heat. If there's more heat flowing in, then there will be a larger temperature difference. Yeah, so a higher temperature difference would give us a faster heat flow. So the temperature difference between the two segments of the rods here is just dt. It's that little tiny temperature difference. And so we can write then that dq dt, the rate at which the heat flows, should be proportional to, and now we have to get the sign right, negative dt. Now I put a negative sign there because if we're interested in the heat flowing this way, i.e. the heat flowing out of the one on the left into the one on the right, then dt, then the sign of the heat, like the heat should be negative, q should be negative. So the amount that the heat, the rate at which the heat flows should be related to the negative difference in temperature, i.e. if dt is large, then you should have a lot of heat flowing out. If dt is negative, then you should have heat flowing in, hence the negative sign. So those are the three primary ones that I have. And then everybody was right at the beginning. There's also different materials. So different materials just give us the constant of proportionality. It's just a number that you would empirically measure that depends on the material type. And you could, in principle, derive that constant of proportionality, but that's far beyond the scope of this class. I actually wouldn't know how to do that. It'd be very complicated and generally not a problem that people can solve. So this is just something that's measured. And so we call that that proportionality constant, we just call it K. It just because. And so, and by the way, a way to see that different materials will conduct heat at different rates is that like, if you think of like ceramic, ceramic is a really good insulator, so it doesn't conduct heat through it very quickly. Whereas like copper or aluminum are very good insulators. So even for the same thickness, the same length, the same temperature difference, ceramic will conduct heat more slowly than copper would. So putting these all together, we get a formula. We know the constant of proportionality. We have three proportionalities here. So we get that dq dt should be equal to, not just proportional because we know the constant. We have a negative sign here, no other negative sign. So we have a negative k, that's our constant proportionality, times the area. And then it's times dt times 1 over dx, which we can combine conveniently into dt dx. So this equation here is what's known as the heat equation. And it's a more general, and it's a specific case of a more general type of equation called a diffusion equation. This dt dx term, this is what's known as the temperature gradient. It basically tells you, how does the temperature change when you move? Does the temperature go down? If so, then dt dx would be negative if it goes down as x increases. And it basically tells you, I mean, it's exactly as it sounds. It tells you how quickly, it tells you it tells you what direction the temperature is changing in, and that will tell you the direction of the heat flow, for example. Now, this is a differential equation, right? Like it has a derivative on one side, a derivative on the other side, but for our purposes, it's generally overkill. We're generally going to deal with steady state heat flow. And what that amounts to is that it amounts to a linear temperature gradient. Or yeah, a linear temperature gradient, meaning, or rather a linear temperature profile, maybe I should write profile, meaning that the temperature gradient is a constant. This just says that the temperature is high on one end, low on the other end, and it's a line between them. If you were to like plot temperature as a function of position along the rod. And so the temperature gradient dt dx would just be a constant, meaning that if you go 2 centimeters to the right, you'll decrease in temperature by a fixed amount. If you go 4 centimeters to the right, you'll decrease in temperature by twice that amount, and so on. And so the end result then is, or rather in this case, where it's a constant, we can write the rate of heat flow from one end to the other as minus k times A. Well, if the temperature profile is linear, if dt dx is constant, then we can just write it as the difference in temperature divided by the length, right? I.e., the derivative of a line is equal to the slope between the two endpoints. So we can just write dt dx as delta t over the length of our conductor, our temperature conductor. And so here, this L, this would be also the distance between the reservoirs. I didn't actually introduce that language, by the way, of what a reservoir is. A thermal reservoir or a heat reservoir is basically just a system that is so large that if you remove any non-massive amount of heat from it, or amount of if you transfer any non-massive amount of heat away from it to something else, its temperature won't change. Like think, for example, think of Lake Erie. It's like a huge lake. So if you put like what would be a good example? Like the heating element from a hairdryer in it, you're transferring heat into it, right? But like its temperature is not going to change in any significant way. So that would be an example of a thermal reservoir or a heat reservoir, meaning that it can just absorb however much heat, or it can give off however much heat without changing temperature. And so we often work with those because that will let us, for slow rates of heat transfer, it lets us approximate it lets us solve for the rate at which that heat is being transferred by using this approximation. If we weren't working with a thermal reservoir, then the temperature of the thermal reservoir would change with time, and so this delta T would be changing with time as well. But for thermal reservoirs on either end of our conductor that's conducting heat, if they're both thermal reservoirs, then their temperatures are constant, regardless of how much heat flows in or out. And in that case, then this delta T is just a number that we can use to just calculate the rate of heat flow. There's a few examples linked in the lecture notes that give applications of the heat equation that I would suggest you take a look at, but conduction is really not that hard to understand. It depends on the difference in temperature, depends on the distance between the reservoirs, it depends on the surface or the cross-sectional area of the thing conducting that heat, and it depends on the material properties. And so this thing just tells us how much heat is, or the rate at which heat is transferred. By the way, this would have units of joules per second, right? Because Q has units of joules, T has units of second. This is also known as watts. It tells us the power transfer from the thermal power transfer, really, from one reservoir to another. So that's the first type of heat transfer, conduction. Conduction is just when heat goes from one thing to another because there's a physical object connecting them, physical solid object connecting them. The second one is convection. Now, convection is a lot harder. Convection occurs for fluids, and fluids, by the way, are liquids and gases. Both liquids and gases are considered fluids. Where the hot particles mix with the cold particles, or diffuse into. The idea is that instead of having your hot particles in one place and your cold particles in the other place, and then the hot particles make the particles near them hotter, and then that slowly transfers to the cold particles, really, because fluids and gases are not stuck in a rigid structure, they'll just mix all over the place, and they'll come to an equilibrium, which involves transferring heat from one place to another. Now, This particular phenomenon is notoriously hard to handle. In fact, it's so difficult to handle that this is a subset of a problem that if you could solve, you'd win $1 million. It's known as the the problem you'd have to solve is the problem you'd have to better analyze and have a better understanding of is known as the Navier-Stokes equation. And there's a business about proving unique existence and uniqueness of that equation. But anyway, if you can solve that problem, there is a prize for you of $1 million. And it's been standing for about 100 years. Nobody has managed to do so. It's a very, very hard problem to solve. However, we can approximate it. The approximate relationship between the temperature difference between your two substances, your hot and your cold particles, and the rate of heat flow is that dq dt is roughly equal to the temperature difference to the 5/4 power. And so this isn't quite Newton's law of cooling, but it's pretty close. By the way, Newton's law of cooling just says that the rate of heat flow is proportional to the temperature difference. This isn't that because it has a 5/4. It's not directly proportional. Now, in general, convection is faster than conduction in a particular sense of the word. And the reason is just because convection has delta T to the 5/4, whereas conduction has delta T to the 1. And delta T to the 5/4 is greater than delta T to the 1 for temperature differences of more than 1. Now, the reason why convection is faster is kind of intuitive too, right? Like imagine you have two different scenarios. You have two ice cubes that are at different temperatures. Maybe one's at -10 C and the other one's at -50 C. And you just put them next to each other. Eventually, they'll come to the same temperature via conduction, but it'll take some time. Whereas, on the other hand, if you take two buckets of water, the same amount of H2O, but now it's in the liquid phase, one of them's hot and one of them's cold, same temperature difference of 40 degrees Celsius, say. Maybe one's at 10 degrees Celsius, the other's at 50 degrees Celsius. And then you just mix those buckets of water. Well, that's going to come to equilibrium much faster than the two ice cubes next to each other will. And that's because convection, this mixing process, occurs much more quickly than just the slow march of jiggling. So, and that's why convection ovens, by the way, are so effective at heating objects, because they can transmit heat a lot more quickly than standard, well, actually, for regular ovens, they're actually radiation ovens, but that's a separate issue. So in fact, that actually segues us nicely to the third type of temperature or of heat transfer, which is radiation. Now, this is not the radiation that you should be afraid of. In fact, really, you shouldn't be afraid of radiation anyway. This is the way that heat is transferred that warms Earth. It's warmed by solar radiation. It's not how you spell solar. And the radiation in solar radiation doesn't mean like radioactive. It just means something that radiates. Now, the reason how we know that the way the sun heats the Earth is by radiation is because, well, it can't be the other two, right? In order for the sun to conduct heat to the Earth would require that the sun is like touching, like there's a piece of metal on the sun that's touching the Earth, right? That's certainly not happening. There's no long rod that connects the Earth and the sun. Similarly, there's no gas, there's no fluid between the Earth and the sun. It's just vacuum, right? There's nothing to convect energy from the sun to get to the Earth. The only way that it can get there is by light waves. This is what we mean when we say radiation. At least in the context of heat transfer. So the question is where do these light waves come from? Well, they come from the sun, but like, what about the sun? Where in the sun do they come? They come from vibrating electrons, as we well know. Electromagnetic waves are produced when things with charge, namely electrons, vibrate a lot or move. When they move, when they have non-zero acceleration in particular, i.e. if they're moving back and forth, their acceleration is not zero, or if they're just moving in random directions, their acceleration is not zero, they produce radiation. They produce light waves. So the question then is what causes the vibrating electrons. So we already know that light can cause vibrating electrons. Like if you hit an electron with light, it might cause it to vibrate. Well, one way that you can create vibrating electrons is just by random motion due to thermal energy. So thermal energy can be described as a macroscopic view of the the energy associated with random motion of microscopic subatomic particles. And so really, if a thing has thermal energy, that means that all of the particles in that that make that thing up, namely like the sun would be an example, all of those particles are randomly jiggling, randomly moving around. The electrons are moving and so on and so forth. And so, and in particular, the more thermal energy a thing has, the more its particles are jiggling. That kind of, hopefully that makes sense. That's how we talked about thermal energy to begin with. At least I think, did I actually talk about that? Did I use the word microscopic? Yeah, okay, I did. So what this implies is that if hotter things have more jiggling of their electrons, then that would mean, or that should suggest, that hotter things should emit more radiation. And this is true. And in fact, you know this is true, right? You guys have all seen like what happens when you heat up metal really, really hot. It starts to glow. And if you heat it up even hotter, it'll glow even brighter. This is precisely radiation. This is radiation as a result of increasing the thermal energy, or thermal radiation. However, the relationship between the temperature that something has and the amount of radiation that it has is not really obvious. We know a formula for it. It was derived back in the late 1800s, and I'm going to give it to you. But deriving it's a little bit less straightforward than it is for than it is in the case of conduction. But the important thing here is that we don't just care about whether something is hotter relative to another thing, right? We just care about what the absolute temperature of an object is, right? Because the absolute temperature should be the thing that tells us how much motion there is, i.e., like if something's at 0 degrees Celsius, why would that mean that there's zero motion, right? We can't just use a relative temperature scale is what I'm getting at. We have to use an absolute scale because the absolute scale actually tells us how much thermal energy a thing has. So let me just jot that down. Absolute temperature scale, by the way, is typically done in Kelvin, but I think there's also one called the Röntgen, or no, that's for, no, there's one called, it's the equivalent of the Kelvin scale, but for Fahrenheit. I don't remember what it's called though. And it doesn't matter because nobody uses it anymore. So we need to use absolute temperature to measure how hot something is, at least as far as the amount of radiation that it emits. So this all leads to something known as the Stefan Boltzmann Law. So the Stefan Boltzmann Law is a derivable but empirically observed. So it's a law because it was empirically because it was experimentally observed first, and then it was derived from first principles. That's why it's a law. But the Stefan Boltzmann Law tells us that the rate, or describes the rate at which heat flows out in the form of radiation from an object. So it says that dq dt, that's the rate of heat flow, and this is an absolute value because we're talking about heat flowing out. This is equal to sigma, I'll tell you what that is in a minute, times E times A times T to the 4th power. So I have to tell you what all of these things are. So this sigma, this is just a constant. It's a measured experimental constant. It is, sigma is 5.67 times 10 to the -8th, and it has units of watts per Kelvin to the 4th times meters squared. Just is. It's known as the Stefan Boltzmann constant, or yeah, that's what it's known as generally. This E, that's a little bit different. This E tells us how well does the object emit light.
Yes.
Now you might say, well, why wouldn't all things emit light the same way? Well, maybe they do, and so maybe this is just the same number for everything. But in principle, this would be like a material property, right? Like maybe some things are better at emitting light than other things because their electrons are more free to jiggle around or whatever. In principle, that's possible. This A here, A tells us the surface area that's of the thing that's doing the emitting. And this should kind of make sense too. You have a whole bunch of electrons jiggling in an object. The only ones that are going to emit light that goes away and doesn't just get reabsorbed by the object are not the ones that are in the center, because those are going to jiggle, emit light, and then it's going to be reabsorbed by other electrons. The ones on the surface of your object, think the surface of the sun or the surface of a really hot iron bar or whatever, those are the electrons that are going to emit light, and some of it's just going to go out and never come back. So the more surface area it has, the more light it can emit. And then finally, this temperature, this is just temperature, but it's the temperature of the object. And importantly, note that it's a fourth power. So it increases very, very quickly with temperature. If you double something's temperature, absolute temperature, of course, you will multiply the amount of heat that it radiates by 16. So it's a huge, like radiation can be a very effective way to transmit heat if your temperature is sufficiently hot. Unfortunately, maybe not unfortunately, this constant sigma is very small. So on everyday scales, things don't emit a whole lot of radiation just because their temperature is only, a few hundred Kelvin at most, and this sigma is very small. But everything does still emit radiation. So now we've already talked about light, and we're talking about things emitting light. So you could reasonably ask, what frequency is emitted? Right? That would be a reasonable question to ask. We know light has frequencies. So if something is, no, E doesn't have units. It's just a number. It's actually just a number between 0 and 1. It tells you if it's 0, then a thing can't emit any light. And if it's 1, it's perfect. It's perfect at emitting light. It's just a characterization. Basically, this tells us how rough is the surface. And when I say rough, I mean that in a really loose manner. It's like how rough on like an atomic scale. So it can also be viewed as like how shiny or how reflective the surface is. Right, no, that's a good question though. Right, so you can ask what frequency is emitted. That's a reasonable question to ask. And it turns out that all frequencies are emitted, but the amount of each frequency depends on the temperature. And again, your intuition probably should agree with this, right? You know that if you start off with something that's really, that's hot, but not like blazing hot, like a piece of iron, it'll glow like a dull red. And as you heat it up, its color will change. And that's just because the frequency of the light that the object emits depends on the temperature. So as the temperature increases, it emits a different range of frequencies. And so its color is going to change as its temperature changes. Now, at normal temperatures, and the reason why we don't see this, normal temperatures meaning like, the range of human existence, maybe 0 to 100 degrees Celsius. Most of the light, and by most, I mean like nearly all, is infrared. And we don't see infrared, and that's why we don't see everybody glowing. But if you put on infrared goggles, then you actually can see people glowing because you're detecting the infrared radiation that they're giving off. So what we've discussed so far is that everything will be emitting radiation. The amount of radiation that it emits, or everything will give off heat in the form of radiation, and the amount of radiation and heat that it gives off depends on its temperature, depends on things like surface area, how atomically rough it is, and so on. And the color, the frequency of the light that's emitted depends also on the temperature. And so if you increase the temperature, the center of the frequency spectrum goes up. So as you increase the temperature, you have more and more high frequency waves that are emitted. So you might say, okay, well, that's great. But we also know that things absorb radiation, like the Earth absorbs radiation. So you might ask, well, how does that work? Like if you want to bring two things into thermal contact, one thing will emit radiation, they can't both be emitting radiation. So can we understand how the radiation is absorbed? The answer is yes. It turns out that every object that can emit also absorbs. And every object can emit radiation, except, I suppose, unless it's emissivity, which is that number E. Oh, I should tell you that. This number E, this is the emissivity. I'm going to spell this wrong. Emissivity? It's just it's a substance, or it's a sample property. Like it's a property of the thing that you're trying to calculate it for. So every object that can emit radiation can also absorb radiation. And so, in fact, the way that it absorbs radiation, or the rate at which it, how do I want to say this? The emissivity E tells you what percentage of radiation that hits that object is absorbed. So if a thing has an emissivity of 1, then that means that all of the radiation that hits it is absorbed. That, and I'll talk about this in just a minute, but that would be something that absorbs all light. Now, what does that look like from a human perspective? It would look like something that's black, because all of the light that hits it, none of it's reflected, all of it's absorbed. So things that have an emissivity of 1 have to be more or less black. Now, just before we continue to talk about that, if an object has a temperature T, and this is important, if an object has a temperature T, and is surrounded by an environment with a temperature T sub S, think like the air around you. Then the rate at which heat enters the surroundings i.e. leaves the object, and I know I'm writing this out in long form, but it's important, is dq dt. This is the rate at which heat enters the surroundings. So if we wanted to figure out the rate at which heat leaves the object in question, we would have a negative sign. So this is sigma times E times A times T to the 4th minus TS to the 4th. Now I leave it up to you guys to figure out why it has this formula, but the basic gist is that, well, the object is going to emit this much, but the object's also going to absorb some amount from the other, from the surroundings. Now the surroundings are going to absorb all of the heat that the object gives off, but so the surroundings, you might say, have an emissivity of 1. It absorbs all of the heat, but the surroundings are also going to radiate. And so they're going to radiate a certain amount, which will then be reabsorbed by our object. And so while the object is emitting radiation, it's also absorbing some radiation. So the amount of heat would be basically the difference of the amount that it absorbs, or the difference between the amount that it gives off and the amount that it absorbs. You can see more details on this in the Libre text that I suggest you take a look. Now, it's also true that two objects that are separated by a large distance, like the sun and the earth, can come to a form of equilibrium. Now, they're not necessarily, it's not necessarily a closed system. So when those objects come to thermal equilibrium, that doesn't mean that they have the same temperature. Like the earth and the sun are in thermal equilibrium, or are in thermal equilibrium, but they're not the same temperature. And that's basically because not all of the heat that comes from the sun gets to the earth. If that were the case, and they were in thermal equilibrium, then they would be the same temperature. But the sun wastes a lot of heat that it gives off, goes in other directions, not all to the earth. So that's why, even though they're in a sort of equilibrium, meaning that the relative temperatures aren't changing significantly, their temperatures aren't the same. So that's why, so in the lecture notes, you'll see that equilibrium is in air quotes, because it's not actual thermal equilibrium. Now there's just one more thing I have to define, and that is a perfect absorber slash emitter, i.e. something that's black, is known as a black body, or a perfect black body, or an ideal black body. And when this happens, this says that the emissivity is 1. And so the idea here is that if something can absorb light perfectly, then basically by symmetry, like absorption is just emitting in reverse, that thing should also be able to emit light perfectly. So in the real world, nothing's really a black, well, okay, there's one thing that's a black body, and that's black holes. But besides black holes, nothing's truly a black body, but there are things that are very, very close. And by the way, black bodies aren't necessarily black. They're just black when they're cold. But like, for example, if you took a perfect black body and then heated it up a lot, it would start to glow because it's giving off radiation. The black body basically is just a way of, it's just a name. And where it came from, I could speculate, but I don't think that that's actually a worthwhile use of our time. So those are the three ways that that heat is generally transferred from one thing to another: conduction, convection, and radiation. We're not really going to spend a whole lot of time on convection just because it's hard and we don't have a whole lot of formulas for it, but it's a useful concept. And then conduction and radiation, we can work with a lot. And those ones are particularly useful too, or particularly useful too. Like figuring out things like radiation, that helps us determine, for example, how large do the radiators, hence that's where the word radiator comes from. How large do the radiators have to be on a satellite in order so that it doesn't overheat from the sun? Because when the sun will hit the satellite and heat it up, the radiator or the radiators on the satellite have to cool it down enough that it doesn't overheat. Otherwise, that heat doesn't go anywhere. It'll just stay the same temperature. It'll just keep increasing in heat. As it gets hotter, it'll emit more and more radiation. And so you could figure out where that balance point is for a given configuration. So we're going to change gears now slightly. We're still talking about thermodynamics, but we're going to start to talk about a specific system. We're going to talk about the thermodynamics or thermodynamic states and ideal gases. So for the most part, the things that we're going to consider, or most systems that we're going to deal with in this course, like on homework or on exams, will be ideal gases. And that's because we have the best hand, like with the tools you guys know. I can't talk today, sorry. With the knowledge that you guys have, ideal gases are basically the only thing that we can solve exactly, that we have complete understanding of. You could in principle do more complicated systems, but that requires more that you guys might just not have. So I need to give you a key definition, which is super important. I need to tell you what a thermodynamic state is. So a thermodynamic state put an underline there to tell you that's the thing we're defining, is the macroscopic condition, macroscopic meaning observable on a human level, microscopic meaning you need microscopes and stuff to see it. It's the macroscopic condition, is it conditions? Yeah, macroscopic condition of a system describable with just a few measurable quantities. So the idea here is that there is the actual full state of a system. Like, for example, if you have a box filled with gas, if you wanted to completely know the state of that system, you'd have to know the location and speed of every single particle in that gas. But we usually don't care about that. Usually we only care about the thermodynamic state. The thermodynamic state is basically the macroscopic emergent properties of the microscopic details. So these would be things, and we'll talk about them, but these are going to be things like temperature or pressure, right? So just as a quick aside, in thermodynamics, and this is not generally true for more advanced thermodynamics courses, but in what we're going to talk about, we only work with equilibrium states. Now, equilibrium states are states that if left to their own devices wouldn't change. They wouldn't change their macroscopic properties. And the reason for that is because if we considered non-thermodynamic or non-equilibrium states, then we would have really complicated things, and we'd have to deal with things like convection. Like, for example, if you had a box of gas where one side of the box was really, really hot and one side of the box was really, really cold, well, now you can't just talk about the temperature of that gas or the pressure of that gas or whatever, because now, as time goes on, they're going to mix and they're going to even out. Once they fully mix together, then it would be in the equilibrium state. But in the situation where half the box is hot and half the box is cold, that's not equilibrium, because those properties, the macroscopic properties, are going to change with time. So an equilibrium state is basically something that you can leave alone, and so long as it doesn't interact with the environment, it'll just stay the way it was. Right. So I've mentioned this business of macroscopic or measurable quantities, so I ought to tell you what they are. So these things are called state variables. Kind of makes sense. They are variables that describe the state. So these are the quantities above, the measurable quantities above. And so the state variables are pieces of data that describe the conditions of the system. Temperature would be a great example. So for example, for a box containing a gas, what things would be measurable? Well, we could certainly measure pressure. We can measure the volume because the box has a volume. We can measure maybe temperature, or maybe even the number of moles, or the mass, the number of molecules rather. That would be a property that stays the same, right? And it just is a measure of the system. So there's just a whole bunch of things. Like any of these things are state variables. Like color would be a state variable. Doesn't change with time. It's just a macroscopic property of the system. Mass, other things would be like, and we're not going to get into this, but like the magnetization would be another example. Like there's just basically macroscopic things that you can measure. Now, I already listed off a whole bunch of examples, but the ones that are most standard, oops. And I just want to write this down so that you have the symbols that we use are pressure, given a capital P, volume, given a capital V, temperature, given a capital T, internal energy, also known as the thermal energy, given the letter U, and the number of particles. Number of particles is given the letter capital N for number. That's not a very good looking N. There we go. So those are the state variables that we're going to use most often in this class. We're going to introduce a few more later in the course, but these are going to be the primary ones that we're going to see for the most part. Now, so these are examples of state variables. What about things that aren't state variables? So things that aren't state variables would be thermodynamic variables or symbols or quantities that don't just depend on the properties of a system. So these would be things like work and heat. And the reason is because these depend on the process that the system is undergoing. The amount of heat leaving the system depends on what the system or how the system is interacting with its environment. It doesn't just depend on the system itself. So these might be called process variables. So, and this is just to say, a state variable, another way to view this would be a state variable is a property that you can use to describe the system itself. It is an intrinsic property of the system, whereas a non-state variable is a property, or is a property of a situation. Now, it doesn't mean that these things aren't useful. Thermodynamics basically is the study of how work and heat interact with the state variables. So these things are useful. We just don't call them state variables for a reasonable reason. Namely, the relationships between work and heat and the state variables depends on what's happening to the thing. Whereas the relationships between the state variables themselves, like P, V, T, U, and N, those are just property, like the relationship is just a property of the system itself. So before we continue, I want to give a quick aside about what pressure is, because you may not have seen it before, and I don't want to assume. So pressure is basically the notion that, or pressure is, I mean, most formally, pressure is force divided by area. But more importantly, it's kind of a random force. So for a fluid that's in an enclosed space, the molecules are moving around randomly, right? They're just going every which way. For liquids, for gases, if it's in an enclosed space, they will just be moving around randomly. And the important point is that when particles randomly hit the walls of its container, they apply a force. I.e., because the particle doesn't pass through the container, pass through the walls, it bounces off, its momentum changes. And because its momentum changes, it means that the wall applied a force to the particle. And so from Newton's second law, we would know, or Newton's third law rather, we would know that the particle also applies a force to the wall. And so that force, like the conglomerated force of all of the particles bouncing off of all of the walls, that in a sense is how we measure pressure. Now, because we don't want the force, because we don't want the pressure or this quantity to be measured depending on how big the walls are, because if your walls are really big, then you'll have more force applied to it because you have more particles bouncing into it. What we end up doing is we end up dividing that force that's applied to the walls by the surface area of the wall. So the end result is that we define pressure to be force divided by area. So you take the total force applied by all of the particles on all of the walls, or on each of the walls, and you divide it by the area of those walls. So the units for pressure would be newtons, the units of force, divided by the units of area, square meters. This has a name. It is called the Pascal, named after the French fellow, and it's abbreviated PA. 1 atmospheric pressure is the pressure that the molecules in the air apply to, say, the ground or your hands or your head or whatever, just by existing, because there is pressure. And that works out to be about 101,000 pascals. And you could convert that to things like pounds per square inch, PSI. That would be a measure of pressure. Another one is bars, I think. Bars is another one. And it's just an old unit. And I think 1 bar is like 1 atmosphere worth, so it's like 100,000 pascals or something. Anyway, there's some relationship, but for the most part, we're just going to use pascals because it's the most commonly used. Okay, so that's the aside. That's what pressure is. So now that we know what pressure is, we can actually talk about the state variables. You guys know what volume is. It's the volume that the substance takes up. Temperature would be its temperature. Internal energy is just the thermal energy it has, and the number of particles would be how many particles are there. So it turns out that for an ideal gas, and we'll talk about what an ideal gas is in a minute, all of the state variables, well, all of the state variables that I've mentioned, things like color wouldn't be affected by this. All of the state variables can be determined by just 3 of them. Now, that seems unusual because why would it have to be that that you wouldn't need that there would be any relationship between them, right? You could imagine changing volume without changing the temperature, or you could imagine changing the number of particles without changing the pressure, and so on. Like a priori, you might say that they're not related, but the point is that for ideal gases, experimentally, this phenomenon is true, that you only need to know 3 and you can figure out the others. And so usually we choose the 3 that we choose. This is not always, but usually we choose pressure, temperature, and volume as the 3 state variables, and we calculate the other ones given those. And like I said, any three of the five would work, but these are the most convenient. So the question then is how do we determine we need some way to figure out if these three determine the other two, then there should be some relationship there. And the way that we do this is by using something called an equation of state. And there could be more than one, so I'm going to write equations of state. So equations of state, equations of state are equations that relate state variables to each other, even when the state itself changes. Now, what do I mean by that? Like, how could they relate the state variables to each other when the state changes? The point is that if a system is described by these three variables, and then we change one of them, the equations of state tell us how the others are going to change in a corresponding way. Put another way, the equations of state are properties of the type of system. So an ideal gas is going to have a specific equations of state that describe all ideal gases. And then if you want to find the state variables for a particular ideal gas that you're examining, you only need to know a few. And then you can plug those into the equations of state to find the other ones. So for example, the pressure could depend, or how do I want to write this? The pressure could change, or it would change, if the volume or temperature or number of particles changes. I.e., pressure would be, and by the way, the picture here is we're imagining that instead of using pressure, temperature, and volume, we're using temperature, volume, and number of particles. So the idea is that if any one of those three things change and the rest stay the same, then in principle, pressure should change. And that kind of makes sense. You guys should have this intuition. If you take a box and you just make it smaller, like if you squeeze down on a balloon, the pressure inside that balloon is going to go up. So somehow volume is related to pressure. And similarly, you guys might be aware from like filling up car tires or whatever, that the temperature of a gas is related to the pressure. And even more obvious, if you have the same volume and the same temperature, meaning the same amount of movement, but you increase the number of particles in that box with that temperature, then you'll have more particles bouncing off the edges, so the pressure would change. So the point is that the pressure is going to be determined completely, at least in an ideal gas, by these other variables. So that means that we can write the pressure as a function of the volume, the number of particles, and the temperature, i.e. there is some function f that would tell us how pressure relates to these other things. And the actual function f depends on the type of the system, the type of system being described. It might be one thing, for example, like this function might be one thing for, say, ideal gases, but if you're describing a different type of system, maybe you're describing magnetic liquids or something, then it would be a different function. And so this would be an example of an equation of state, because it tells us how the state variables relate to each other. I want to repeat this just to make sure that it's 100% understood. These equations of state are for an entire class or entire type of system. So while two different samples of ideal gas might be different, like maybe one sample is argon and it takes up 30 cubic kilometers and is, has like a pressure of 0.2 pascals, and the other one is like a really dense mercury gas or something. Like as long as they're both still described by as long as they can both be described as ideal gases, then they still both obey the same equations of state. They'll just have different state variables plugged in. So we're going to consider the simplest case, which is the ideal gas. And that's the one that we're going to spend the most time on. This is the simplest example of, or the simplest type of system. There are other types of systems that we have the mathematics to do, but this one's just the simplest. So let's talk about ideal gases. So what we're going to do is we're going to consider a system of a gas in a box. It's just a regular old box. It's sealed. It's just a gas in there. And so we can measure a lot of state variables. We can measure, for example, we can measure volume because the gas takes up the whole volume of the box. So it's just the volume of the box. We can measure the temperature by sticking a thermometer in. We can measure the pressure by putting a pressure gauge into our box. We could measure the number of particles by, say, weighing the box, figuring out how much mass the box or the gas has, and then dividing by the mass of each particle. So there's a whole bunch of different things that we could determine, that we can measure empirically. Like you could get out some tools and actually do this measurement. Now, by changing the size of the box, by changing the number of particles in the box, by changing the pressure of the gas in the box, we can actually just do this experimentally. We can figure out this relationship between the state variables. And this was done, I want to say, in the late 1700s. But I don't know off the top of my head. So the equation of state that that can be experimentally determined is that P, the pressure, which is a function of the number of particles, sorry, let me get this in the right order. The volume, the number of particles, and the temperature has the relationship that the pressure is equal to a constant, Kb, times the number of particles times the temperature divided by the volume. This constant, by the way, this is Boltzmann's constant, or not Boltzmann's constant, but the Boltzmann constant. Actually, am I spelling that right? I feel like there's two N's at the end, but I'm not sure. Let me check. Yeah, there's two N's at the end. Okay. By the way, same Boltzmann as before. The dude was a big deal. Same dude as in the Stefan Boltzmann Law. This constant is 1.38. It's just a number that's experimentally determined, by the way. 1.38 times 10 to the minus 23rd. It's a very small number. Joules per Kelvin. It's just a constant. And so this is the relationship that we observe. We observe that the pressure is inversely related to the volume. It's proportional to the, or inversely proportional to the volume, proportional to the number of particles, proportional to the temperature, and the constant that determines those proportionalities is Boltzmann's constant. This is just something that we have experimentally determined. And you guys could go, if you had, if you had the right tools, you could just do this yourself. You could have experimentally determined this yourself just by taking a whole bunch of measurements, plotting data, and you find that, if you double the volume, the pressure doubles, or sorry, if you double the volume, that the pressure halves, and if you quadruple the volume, the pressure decreases by a factor of 4, and so on. This is just observably true. Now, just as a quick note, we'll get there. Just as a quick note, in this formula, we have to use absolute temperature, and that's because there's no delta T involved here. There's no relative temperature. So this temperature here is measured in Kelvin. It's not measured in Celsius. It's not measured in Fahrenheit. It's measured in Kelvin, and it has to be measured in Kelvin because we need that and think back to where we were first talking about pressure versus temperature. We need that when the temperature goes to 0, the pressure should go to 0. That's how we defined the Kelvin scale. So if you plug in T equals 0, you should get pressure at 0, and that's just true. So we have to use the absolute scale here. Now, let's back up a little bit and ask about what this ideal means in ideal gas law. So in this case, it means that the gas molecules don't interact in any appreciable way, meaning that they don't bounce into each other, they don't attract each other, they don't repel each other. They just pass right through, unbeknownst to each other. And you might say, well, that's not true at all. Like, they can't just pass right through each other. That doesn't make any sense. And, you know, you'd be right. Gas molecules can't pass through each other. But gas molecules are so small, and the distance between them is so big, that this is actually a really good approximation of most gases. Most gases at most normal, quote unquote, normal temperatures, like temperatures that humans experience, behave like ideal gases. That's just true. Now, the degree to which they behave like ideal gases varies. Like if you have really, really heavy molecules or really, really big molecules that make up your gas, it's less likely because, you know, they're more likely to bounce into each other and they're moving more slowly, so they have more time to attract and repel each other. But like the point is for most gases, like, you know, carbon dioxide or neon or oxygen or nitrogen or whatever, all of those everyday gases, those are all nearly perfectly approximated as ideal gases. Now, so this is a useful equation of state, but it requires that you know exactly how many molecules there are, which isn't exactly the easiest thing to do. And so instead, we can express this formula. We can express this formula in terms of the number of moles of the gas. Number of moles in the gas, and that's abbreviated by little n. By the way, just so then you guys can have it in your notes, this is written as P equals KB times N times T over V. This is known as the ideal gas law, or it's one formulation of it, just so you guys have this. It's a law because it's experimentally determined, and it's for ideal gases. So before I can explain what the number of moles of a substance means, I ought to explain what a mole is. So in general, actually this is just by definition, 1 mole of a substance, it's an amount, is equal to roughly 6.02 times 10 to the 23 units of that substance. So if we're talking about a gas, a mole of that gas, like a mole of hydrogen, or let's use helium, a mole of helium would mean that you have 6.02 times 10 to the 23 atoms of helium. A mole of moles, like the small burrowing animals, would be 6.02 times 10 to the 23 small burrowing animals. A mole of ideas means that you have 6.02 times 10 to the 23 ideas. The reason why we use moles is because it's a way of bringing it's a way of bridging the gap between atomic, like tiny atomic and molecular sizes to macroscopic sizes. So a mole of gas is like this much gas. It's like a macroscopic amount of gas. It's not too big, it's not too small. It's a macroscopic amount of gas. And so we use moles just because it keeps the numbers on a human scale. This number, by the way, it's known as Avogadro's number. And it is given the symbol N sub A. So Avogadro's number is equal to 6.02 times 10 to the 23rd. It's literally just a number. Like maybe you would write units, you would say 6.02 molecules or 6.02 units per mole, but you don't have to. This is just a number of things, right? And so written in terms of the number of moles of a thing, that means that the number of things, n, say the number of molecules or particles or units or whatever, should be equal to the number of moles of that thing times Avogadro's number. If you have 2 moles, that means that you have twice that many Avogadro's number of particles. So here, this is the number of things, particles, units, whatever. This is the number of moles. So you can almost think of a mole as like a dozen. Like if you have 5 dozen, that means you have 5 times however many things there are in a dozen, which is 12. So you'd have 60 things. A mole is just a really, really big version of that. And so this tells us, like, if you have 5 dozen, you multiply 5 by however many things are in a dozen. So 5 times 12 is 60. So you'd have 60 things. If you have 5 moles, it means you have 5 times Avogadro's number of things. So written in terms of these symbols, i.e. written in terms of the number of moles in Avogadro's number, the ideal gas law becomes P equals, well, we need to replace n with little n times Na times, so it was P equals KB. Yeah, I'll do this. I'll do n times Na times KB times T divided by volume. And then we just say, okay, well, Na and KB are both just constants. So we just define, if they're just constants, we can combine them. We define the gas constant, which is just Na times Kb. This is equal to 8.31 joules per mole Kelvin. So I put mole as a unit. It's not really a unit, but it helps you keep track of what this thing measures. This is the gas constant. That's the name that it has if you want to look it up on Wikipedia. It's just another number. It's just 8.31. And so then in terms of R, we have that P equals nRT over V, or perhaps more familiarly, we have that PV equals nRT. And that's probably the ideal gas law that you guys are familiar with. But, you know, they're all the same thing. No, so P equals nRT over V is actually a lot more useful because pressure is usually the thing that we're actually calculating. So being able to know the relationship in terms of V is a lot nicer. And anyway, I prefer to use P equals nRT over V because everybody just hears PV equals nRT and their eyes just glaze over because they're like, oh, that's the ideal gas law. It's Pivner. It's just a thing. But they don't actually understand where it comes from. And so so by not using this one, it forces people to actually think about and understand what they're talking about. Now, at the end of this, or in the lecture notes, there's a whole bunch of examples, and by a whole bunch I mean 4, that you guys can take a look at if you want to, practicing using the ideal gas law, practicing using this this notion of number of moles, and so on. But remember that this is just one equation of state, right? It just tells you how one state variable is related to the others for an ideal gas. If you're not talking about an ideal gas, this equation does not apply. That's just true. In fact, there's another model. Another more complicated model is the van der Waals gas. I believe that actually be pronounced van der Waals. I think he was Dutch. And so the van der Waals gas models the gas as particles, just like the ideal gas law does, but those particles can now attract, repel, and bounce off each other. And so a van der Waals gas is described, or also has a state, or an equation of state, and that equation of state is described by the van der Waals equation. Which again just relates state variables to each other, but in a more complicated way because now our model is more complicated. So the van der Waals equation looks like P plus an squared over v squared times v minus n times b equals nRT. So here, a and n are constants. Sorry, a and b are constants. And a basically tells us how strong the attractive force is. And B tells us basically how big the model says that these hard bouncy spheres are. The idea is like you're treating them like billiard balls, and this B controls, how much they bounce off of each other, how big they are, and so on. And so actually, you can even just take the limit where A and B go to 0. So if there's no attractive force, and if these are treated as point particles that don't bounce off each other, if you make A and B 0, you actually just get the ideal gas law back. But the point is that this is a different and perhaps more accurate model of a gas that is described by certain properties, and this is how those state variables would relate to one another by this formula. Is that right? I may have gotten that formula wrong. We're not really going to use it, so you know what? Let me just be on the safe side. Let me verify that that is correct. Yeah, that's right. Okay. Right. So again, you can just keep coming up with more different models that accurately describe different systems, and you'll end up with different equations of state. The ideal gas law isn't special in that regard. It's just the simplest one. So we're going to change gears slightly. We're still going to be talking about ideal gases. But now we're going to do the second half of thermodynamics. So the first half of thermodynamics, and really like this, it's not like we're going to be done with thermodynamics after this, but the point is thermodynamics is the study of how macroscopic states interact with each other and how they arise from microscopic things. So far we've talked about how things exchange heat, which would be a macroscopic phenomenon. We've talked about how the state variables relate to one another. But what we haven't done is we haven't talked about how these macroscopic quantities arise from microscopic phenomena. And that's what we're going to do. We're going to talk about the kinetic theory of gases. And I don't think that we'll have time to finish it today, but we'll do as best as we can. So like I just said, our goal is basically that we want to think about what happens on the microscopic scale and use that to draw conclusions about what happens on the macroscopic scale. And so what we're about to do is a perfect example of that sort of thinking. So we're going to start with an ideal gas in a box. So we're just going to put it in a cubic box, side length L. And there's just a few molecules here and there, just zipping around doing their thing. Right? They're just doing gas things. And so now we need to, before we can actually start to analyze the system and think about what the motion of these atoms or molecules, how they affect the macroscopic properties, we need to lay out a few assumptions that will be particularly useful. So the assumptions of our ideal gas and of our system are that the particles have random velocities and positions. That's super important because if they didn't, then you could run into situations where like all the particles are in the left corner, and that doesn't happen, and that wouldn't be just like, that couldn't happen for an ideal gas. If that were to happen, then the ideal gas law wouldn't apply. So they should have random positions and velocities. That's one assumption that we're going to make. They should also be describable by an ideal gas. That one should be kind of straightforward. Another one is that, so these particles are going to bounce off the walls and do stuff. We don't want the walls to like heat up from the particles bouncing off of them. We want the walls to just be perfectly rigid and to not absorb any energy, i.e. we want that no energy is lost to the walls. And the reason we want that is because otherwise the temperature wouldn't be constant. The temperature of the walls would eventually equilibrize with the temperature of the gas, which would mean that the temperature is changing. We also want that the walls are atomically smooth. This isn't necessary. This isn't 100% necessary for the calculations we're about to do. It just makes it easier if we make this assumption, and throwing out this assumption later won't ruin anything. The idea is just that when a particle bounces off a wall, we want to know which direction it goes in. And so if it's not smooth, if it's bumpy, then knowing which direction it goes in depends on where the particle hits. And then the last thing that we're going to need, and this might not be so clear yet, is that we want to assume that the gas is monoatomic, meaning it's just a single molecule. So think argon or helium, any of the noble gases, those form monoatomic gases. They don't have bonds. And the reason for this might not be clear yet, but it will become clear eventually. So with those assumptions out of the way, we can now just start analyzing the microscopic phenomenon. So we're going to consider a single particle bouncing off the wall. Or bouncing off one wall. We know that because they don't interact with each other, every particle will eventually bounce off a wall because it's just traveling in a straight line and there's only so far it can travel before it hits something. So the picture here is, let's say you have your wall, right? You have your particle coming in, maybe it has a velocity that way. And so the question is what direction does it bounce off in? Well, hopefully your intuition tells you, oh, let's put some coordinates. Let's make this the plus x direction. Let's make this the plus y direction. It's fine. Hopefully your intuition is right that this thing will come in, hit the wall, and bounce off at the same angle. This is actually the same thing as the law of reflection. But in this case, it's just momentum conservation. So we can relate the initial and final velocities. So here, the initial velocity can be broken down into having two components in the x and the y direction. And the final velocity can also be broken down into having two components, the x and y direction. So because none of this energy is lost to the wall, remember from 9a, when energy is conserved in a collision, that means that the collision is elastic. And so we can use what we learned about elastic collisions in 9a. We can, in particular, we can determine how the initial and the final velocities relate to each other. So from the elastic collision, we have that the final velocity in the x direction is equal to the negative initial velocity in the x direction. I'm using O instead of I for reasons that will be hopefully clear later. And the final velocity in the y direction is unchanged. It's the same as the initial velocity in the y direction. And these are just a result of the fact that it's an elastic collision. Basically, it's bouncing off of something this way, so it's only going to affect the left-right movement, right? It's not going to affect the up-down movement. So with that in mind, we can actually figure out how the momentum changes. This is going back to 9a, so put on your 9a hats. So the momentum change can be determined also easily. The change in the momentum in the x direction is just the mass times the final speed in the x direction minus the mass times the initial speed in the x direction, which, because the final speed is the same as the initial speed, this has magnitude, oops, I'm going to put magnitudes everywhere, of 2 times the, let me move this back, I'm running out of space, 2 times the mass of the particle times the magnitude of the speed in the x direction. I'm just going to call it Vx because the speed in the x direction is the same before and after. It's just the direction is different. Should it be Voy? Yeah, yep. You're right. This is just the speed in the x direction. And it's the same before and after, it's just changing directions. So that's why it can do that. And then similarly, the magnitude of the change in momentum in the y case, well, the initial and the initial and final velocities in the y direction are the same. So this is just 0. So we can actually, once we know how the momentum changes, we can actually figure out the impulse on the particle from the wall. Remember, impulse is just the impulse from the impulse momentum theorem is just equal to the change in momentum. But it's also equal to, by definition, the force, I'm going to put magnitudes around all of this, times the duration over which that force is applied. So this would be like how long the, well, actually, I'll get to that. So just remember from 9a, that impulse is force times duration. So this would be delta px, just from the impulse momentum theorem. So this should be equal to 2 times m times vx. So far, so good. So we've so far so what we've established is that the force times the duration, or perhaps just the impulse, is related to the speed that the particle hits the wall with. Now, this tells us that the force on the particle from the wall can be written, again, using the impulse momentum theorem, f sub x is equal to 2m v sub x over delta t. Now we have to ask, so we know that this collision is going to take place very quickly, but we're really interested in averages here because these are happening trillions of times per second. So we just want to know how frequently or how much time is it between collisions between the particle and the wall, right? Because if we could figure out that this particle is going to collide with this wall 5 times per second, then we could say that the duration is roughly 1/5 of a second. That's how long that on average, or that is the average force that's applied to this particle. And that's relatively easy to figure out. This particle hits the wall hits this wall in particular every time it travels to L, a distance to L in the horizontal direction. The reason is because the cube has a side length of L. So it'll hit the wall, go back, it'll take some time to do it, but it'll move back to the other side of the wall eventually, and then it'll bounce off and then come back. So by the time it has traveled 2L in the horizontal direction, then it will hit the wall again. Now, how long does this take? Well, we know the horizontal speed. V sub x is, well, the speed is just V sub x. That's the horizontal speed anyway. So the time, the round trip time, delta t, is 2L divided by V sub x. So then what's the upshot? The upshot is that the average force on the particle from the wall, I'm going to put average there, is 2m v sub x divided by 2L over V sub x, which we can rewrite as just m times Vx squared divided by L. And by the way, the average force in the y direction from this wall is 0. Okay, so this tells us the average force on that particle from the wall. But we can use Newton's, oh, that's third law, not second law. I need to fix that in my notes. Otherwise, it'll be awfully embarrassing because I got the numbering wrong. From Newton's third law, this tells us that the average force on the wall from a single particle is the same amount. So the average force from a particle labeled I, V from, average force, because there's a trillion particles, right? So you can label each one with a number, and then the force from that one would be whatever it is, right? The average force from a particle labeled by I, the average force, sorry, on the wall we're going to call it particle I, where I is just a number, so particle 5, particle 2,386, so on, is given by, well, and here I'm going to drop the magnitudes because it's just because the force is always outwards, right? Because it's always bouncing off in the other direction. It is m sub I times v sub I in the x direction squared divided by L. That is the average force on the wall from particle I. So the total force on the wall is, well, it would be the force, the total force would be the sum of all of the forces from all of the particles. It'd be the sum over I, f sub I. This would be 1 over L times the sum of m sub I, v sub I, x squared. Now we know that the pressure, and I know I'm going through this quick, but this is, the fact that we can derive this is super useful. We know that the pressure should be equal to the force divided by the area, right? That's how pressure is defined. The pressure on the wall should be the force on the wall divided by the area of the wall. So that says that pressure should be equal to F divided by L squared, i.e. it should be 1 over L cubed times m sub I, v sub I, x squared, summing over I. But there's nothing special about x. If we had chosen a different wall, we would have gotten a different direction. We would have gotten y or z. So the pressure is also equal to 1 over L cubed, 1 over L cubed times the sum from sum over all the particles of m sub I, say v sub iy squared. And it's also equal to 1 over L cubed times the sum over I of m sub I, v sub iz squared. Like, these are all the same. And so the point is we can add these all up. Oh, and by the way, L cubed is just the volume of the cube, right? So we can add these equations up, that P is equal to this one, that P is equal to this one, and that P is equal to this one, to get that 3P is equal to the sum. It's equal to 1 over V times the sum of m sub I v sub ix squared plus m sub I v sub iy squared plus m sub I v sub iz squared. Or put another way, that's just the square of the vector v. This is just 1 over v times the sum over I of m sub I v squared, not v sub ix, not v sub iy, not v sub iz. It's this vector velocity squared, or the dot product of it with itself. Now this should look awfully familiar because that looks a lot like the kinetic energy. It's just missing a factor of 1/2. So I'm going to multiply and divide by 2, and we get that this is 1/2 m sub I v sub I squared, which is 2 over v sum over I of the kinetic energy of the ith particle. So we've established that 3 times the pressure is related to the sum of all of the kinetic energies of the particle. And that we've done that just by this microscopic analysis. But we can go even further. We know that for an ideal gas, there is no potential energy. And that's because there's no bonds, there's no attractions or repulsions or bouncing. So there's no potential energy. So that means that the total energy, the total internal energy, is just equal to the sum of all the kinetic energies, because there's no potential energies. And remember, total internal energy is called U, capital U. So our formula then, from this microscopic consideration, we have that 3 times P is equal to 2 divided by V times U. Or put another way, that PV is equal to 2/3 U. This is, by the way, this is only true given the assumptions that we've already made. So from the ideal gas law, we're allowed to use the ideal gas law because we're assuming that it's an ideal gas. PV is also equal to nRT. So that tells us that, well, let me write this out. This tells us that U is equal to 3/2 nRT. Again, the T here, by the way, is only in Kelvin. So using the ideal gas law and using this microscopic analysis, we learn that the internal energy is directly proportional. U is directly proportional to the temperature, meaning that if you double the temperature of an ideal gas in a box, then the internal energy precisely doubles. And you may say, well, isn't that obvious? Like, duh, but it didn't have to be that way. What if it could have gone up by, like, what if you double the temperature, then you quadruple the internal energy? It could have been anything. And so the fact that, yes, the internal energy goes up with temperature, now we know precisely how the internal energy goes up with temperature. And that's a lot more information than we had before. And we did that by learning, or by analyzing, the microscopic phenomenon. That's what thermodynamics is about. That's at least what part of it is about. It's about taking some microscopic phenomena and then using that to understand macroscopic phenomena, which is super powerful. Now, that takes us basically almost through to, well, not quite, but there's one more thing that I would have liked to have gotten to, well, a few more things, but one more thing I definitely would have liked to have gotten to, but we'll have to continue with that on Friday instead. In the meantime, I will end lecture here, and I will open it up to questions.